Okay, where we pick up is with an example of the conversion between horsepower and watts. Say a 75-watt light bulb would be equivalent to how many horsepower? we have the conversion factor between horsepower and watts. So we start out with what we are given, 75 watts, and we want horsepower, so that unit goes on top, and we want to get rid of watts, so that unit goes on the bottom. Watts will now cancel, and we should end up with horsepower. 75 divided by 746 is 0.101. Or actually, 75 is only two significant figures, so this should really only be 0.10 horsepower. And so that's how many horsepower is a 75-watt light bulb. So, if you wanted to, you could go around referring to 75-watt light bulbs as 0.1 horsepower light bulbs, because it's the same thing. Also, you could go the other way around. If a car has an engine with 130 horsepower, how many watts would that be? That goes the other way. We now have 130 horsepower is what we're starting out with, and we would use the same conversion factor, only upside down, because this time we want watts as the answer. So you put the side of the equation with watts in it on top and the side with horsepower on the bottom, and we get 130 times 746. Horsepower will cancel, and we get 96,980 watts. Okay, this would also be 96.98 kilowatts because okay, 1 kilowatt for every 1,000 watts. Okay, and that's why they usually, when they do use watts to represent power in something like a car's engine, they will normally use kilowatts, because otherwise you're going to have a really big number of watts. Also, in significant figures, I'll go back and put a decimal point after the 130. So that's 3 significant figures. 746 is also 3. So we can have 3 in our answer. 96.98 means that the 8 would have to go, but that's greater than 5, so the digit before it has to go up by 1, which is a 9, so that has to go up to 0, and means the digit before that has to go up by 1. So 97.0 kilowatts, that's the final complete answer to the right number of significant figures. 97 kilowatts. Okay, so that's the difference between horsepower and kilowatts. Now we come to 2 classifications of energy. Actually, why don't we see a couple more examples of that? We're ahead of schedule, so we have time to do another example or 2. Say a motor has a power rating of 25 horsepower. What would that be in kilowatts? Okay, so first let's go to watts, and then we can go to kilowatts. So 25 horsepower, and there's 746 watts per horsepower. And let's see, this would be 25 times, oops, yeah, 25 times 746 is going to be a really big number, 18,650 watts. And then 18,650, and there's 1 kilowatt for every 1,000 watts. And so that's 18.650 kilowatts. 25 is only two significant figures though, so that's what we need in the answer. So the 18 can stay, but everything from the 6 on has to go. 6 is greater than 5, so that means the 18 has to be rounded up to 19 before we're done. So there we go, 19 kilowatts. Another one is, say a motor is rated at a certain number of kilowatts. And we'll say that a motor is rated at 9.5 kilowatts. And so what would its power be in horsepower? So in this case, we've got kilowatts. So the first thing we have to do is get watts out of it. And there are 1,000 watts for every 1 kilowatt. This, again, is just a matter of knowing what the metric prefixes mean. Kilo means 1,000 of something. So it's 1,000 watts for every kilowatt. Notice the kilowatts cancel. And 9.5 times 1,000 is 9,500 watts. And then we have to go to horsepower. Oh, no, let's put it. 1 horsepower for every 746 watts. So this is going to be 9,500 divided by 746. And that's 12.7345845. You may have guessed, yeah, that's a little beyond what we're allowed to use for significant figures. 9.5 was only 2 significant figures, in fact. So the first 2 digits can stay, but everything else has to go. The first digit we're dropping is a 7. That's greater than 5, so the digit before it has to go up by 1. So 12.73 blah, blah, blah rounds off to 13 horsepower. And that would be the answer to the correct number of significant figures. All right. So those are actually not too difficult. All right, so now we get into classifications of energy. And the 2 major classifications of energy would be kinetic energy, which has usually a symbol of either Ke or E sub K, and, of course, potential energy. Which is symbolized as Pe or E sub P. So to look at them in more detail, kinetic energy is the energy associated with motion. So all moving objects have kinetic energy. And it doesn't matter how small it is or how big it is or how slowly it's moving or how fast it's moving, it'll have kinetic energy of some sort. The unit, because it's energy, will be in joules. But you can use other energies units as well, like for instance calories. And kinetic energy often involves work because work inherently involves moving something. Okay. Because remember, work is equal to force times distance. Distance implies that something has to move in order for work to occur. And when something's moving, it has kinetic energy. And as they relate to each other, the amount of work required to get an object moving at a particular speed is equal to the amount of kinetic energy it possesses once it's up to speed. This is part of the concept that's known as conservation of energy. That is, energy can be transferred from one place to another, or it can change in form, like for instance, from work to kinetic energy, or kinetic energy to potential energy, and so on. But energy cannot be created or destroyed. So the energy has to go somewhere. And in this case, it's going directly from work into kinetic energy. And as it works out, also the maximum amount of work possible is equal to the amount of kinetic energy the object possesses. So if you're going to transform kinetic energy into work, the maximum amount of work that can be done is equal to the kinetic energy that the object has. You can't do any more than that because that's all it's got. So also the amount of work required to stop a moving object is equal to the amount of kinetic energy the object has. And so again, it relates to the concept of conservation of energy. Energy that goes from one place has to end up someplace else. Energy that comes to someplace has to have come from someplace else. The equation for kinetic energy is kinetic energy is equal to 1/2 mv squared. So from this, we can look at the units. The units for mass would be kilograms, and the units for velocity would be meters per second. But velocity is squared. The 1/2, of course, doesn't have any units. That's just a number. When you combine those together, you get kilogram meter squared per second squared. and that's a joule. Okay, so the units make sense. So we keep coming up with joules for all these different quantities. And also, what this equation means is that kinetic energy is proportional to mass if the velocity is constant. So if you've got two different objects traveling at the same velocity, the object that's twice as heavy has twice as much kinetic energy. And that makes sense. Also, kinetic energy is proportional to velocity squared. As long as the mass is constant. So if you're talking about any given object, when you double the speed, you quadruple the kinetic energy. And that's one reason why, say, for example, with cars, braking distance is so much longer the faster you're going. It's because braking distance has to do with basically shaving off the kinetic energy of the car and basically turning it into heat as the brake pads rub against the rotor as the wheel spins, and you're basically turning kinetic energy into heat. It takes so much longer to stop as you're going faster because of this. Kinetic energy is actually proportional to velocity squared. So if you're traveling 60 miles an hour as opposed to 30 miles an hour, you've got 4 times as much kinetic energy at 60 miles an hour than you have at 30. And it takes, I think, it comes out to about 4 times as long to stop at 60 as opposed to 30 for most cars. I mean, it depends on your braking system too, how good your tires are, how much traction there is on the road and things like that. But ideally, yeah, velocity makes a big difference in kinetic energy. Okay, under potential energy, potential energy is stored energy. That's one reason it's called potential energy, is because it's not actually doing anything at the moment, but it has the ability to do something at some point in the future. It's an energy something has based on composition or position or condition. That kind of thing. And because it's stored energy, something has to be done to release it. So, for instance, something like gasoline has a lot of energy stored in its chemical bonds. But in order to get that energy out, you have to burn the gasoline. Otherwise, that energy is going to remain stored in the in the chemical bonds. So that's one example of potential energy, is the chemical energy stored up in chemical bonds. There's the type of potential energy that we usually think of is a particular type of potential energy, and that's gravitational potential energy. Gravitational potential energy is a type of potential energy that something has because of its position, specifically because of its position relative to the surface of the Earth. So this is energy due to position with respect to the surface of the Earth. Or some other reference point. We usually measure potential energy from the surface of the Earth because that is actually a handy reference point. But technically, to be perfectly accurate, it probably should be measured from the center of the Earth because gravity actually pulls from the center of mass of an object. Gravity does not pull from the surface of the Earth, it pulls from the center of the Earth, which makes sense if you stop to think about it, because if gravity pulled from the surface of the Earth, you would not be able to fall into a hole because the hole goes below the surface of the Earth. So if you tripped and fell into the hole, you would bounce right back up to the surface again if gravity were pulling from the surface of the Earth. But it's not, it's pulling from the center of the Earth, so that you'll actually basically keep going until you hit something that stops you, like the bottom of the hole. The reason that we actually measure things like potential energy from the surface of the Earth is because the center of the Earth is kind of hard to get to. And the distance to the center of the Earth will depend on your elevation, for one thing. So you'd have to know what your elevation above sea level is, and then you can add the distance from sea level to the center of the Earth, and that just makes things really complicated. It's much easier just to measure from the surface of the Earth, and that's what we usually do. And so the work done lifting an object to a height above the ground is equal to the amount of gravitational potential energy the object possesses once it's at that height. All right, so again, conservation of energy. Energy that's expended in one place has to go someplace else. So you do work lifting a book up to a shelf. The amount of work you did is equal to the amount of potential energy that the book now has on the shelf versus when it was on the floor. And the amount of gravitational potential energy an object has at height h any given height above the Earth's surface is given, well, on the next page. Okay, on the next page we find out that potential energy is mass times gravity times height. And don't forget, mg is equal to weight, mass times gravity. So it's basically weight times height. Okay, that's the equation for gravitational potential energy. Other types of potential energy have other equations that you can use to calculate them. Also, the SI units, if you want to look at these. M is mass, and SI units, that's kilograms. G is gravity, or technically the acceleration due to gravity, and that's meters per second squared. And H is height. Height would be measured in meters. When you combine all of these together, mass times gravity times height, you have kilograms times meters per second squared times meters. And look what that is, kilogram meters squared per second squared. And that is a joule. So you don't need to know how to go through all of this stuff. You just need to know that energy is measured again in joules. And so the maximum amount of work that an object with gravitational potential energy can do is equal to the amount of energy it possesses. Because again, basically work is a form of energy. And so if the maximum amount of work you can possibly do would be equivalent to all of the energy you've got. Once you've expended all of your energy and converted all of it into work, you can't do any more work. And this brings us to the law of conservation of energy. There are several tenets to this, and they're really all just different ways of saying the same thing. One is that the total amount of energy in the universe is constant. That means it doesn't increase or decrease over time. That's another way of saying that energy can't be created or destroyed. Okay, so energy can't be created or destroyed. Energy can be converted from one type of energy to another. So, potential energy, kinetic energy, work, those are all forms of energy, and you can convert from one form to another. Or energy can also be transferred from one place to another. But again, the total amount of energy in the universe remains constant. Okay, let's see. I think I'll call it there for this segment of the video because these are, now that I'm using the nice new camera, they're bigger. So I better limit it to exactly 30 minutes. And I'll be back in a